Up to now, we've talked about discrete probability distributions and continuous probability distributions, and they were kind of separate. They had their own formulas and definitions and stuff. Well, it turns out we can treat them in a unified fashion by use of the Dirac Delta Function. Well, let me talk briefly about that. Intuitively, we can think of it as a derivative of the unit step. What's a unit step? I use this notation. There's one up here. Argument is t minus alpha or t minus a. And it just means unit step is 0 for arguments less than a and 1 for arguments greater than a. Okay, so what would its derivative look like? Well, for less than a, it's flat. The derivative would be 0. For greater than a, it's flat. The derivative would be 0. And right at a, it's kind of an infinite spike. But if you integrate it, you take a definite integral so that the upper limit of that definite integral is greater than a, you should get 1. Integrate up to a limit below a, you get 0. And as soon as the upper limit goes over a, you get 1. So that's one way to think about the Dirac Delta Function. It is 0 if t is not equal to this a. And its integral over the entire real line is 1. And actually, as long as the limits of your integral contain a, it's also 1. It has this property. In fact, a more rigorous derivation or definition of the Dirac Delta Function is this is the defining problem. This is what makes Dirac Delta Function. I won't get into that, but just look down here. If you put a Dirac Delta Function in with some other function and integrate it over limits that include this minus a, or this a rather, that just evaluates to the function evaluated at a. So if you see an integral like this, as long as these limits contain this a, you just plug in a for t, or a for whatever your variable of integration is. So now that we know how to evaluate an integral involving a Dirac Delta Function, let's talk about mixed distributions. And here's an example. We're an insurer, and we have clients who may or may not have damages. There's an 80% chance that our clients, any given client, will not have damages at all. If they do have damages, we believe it's an exponential distribution such that there's a 2% chance that the damages are over $1 million. I don't know how realistic that is, but let's just say it is. So the PDF would look something like this. There's a Dirac Delta Function notated with this arrow because it's kind of infinite there, but it has a strength of 0.8. That's kind of the notation for that. And it's 0 below, and above 0, it's an exponential decay, such that the area under the curve to the right of 1 million is this 2%, 0.02. So your PDF would look like this. 0 for x less than 0, 0.8 for x actually exactly equal to 0, and this exponential decay for x greater than 0. We can write it in one line using Dirac Delta Function and a unit step this way. So we got to find the a and b. Well, one condition is that the PDF has to integrate to 1. So here's our PDF, integrated over the entire real line. It's got to integrate to 1. How do we integrate this? Well, it's a sum. So it's this integral, that first part. And this second part, because of this unit step, we just integrate from 0 and up. And what is this guy? This guy. Let's go back to that sifting property. Here A is 0, but the F is just a constant. So the answer is just going to be that constant because the integral includes 0. Yeah, these limits include 0. So this evaluate this integrand or this function at 0 or for A equals 0, and you still get 0.8. So that, sorry for that long explanation, but this whole integral out here just evaluates to 0.8. And then this guy we can take, I'm not going to go through that. All that has to equal 1. You do that little bit of algebra and you get a relationship between A and B. A equals 0.2B. So now we've got the other condition that there's a 2% chance that the damages are over 1 million. That means when we integrate this guy from 1 million on up, now we don't have any Dirac Delta functions involved. That integral, and I won't go through that evaluation, but that has to equal that 2%. So from this, we get a B. B equals this little mess, which is about this as a number. And A equals 0.2 times that. So for example, what's the expected payout? Expected value of X. So this would be like the mean payout. Put an X in there times the PDF. We have this. Now we have an X in there. Plus this part. We know the A and B now. Because of this X in here the A is 0. You plug in 0 for X, you get 0. So this whole front part is just 0 now. And to evaluate this latter part, I used the Laplace trick, talked about it in another video. The Laplace of, this is like t e to the minus pt. Laplace transform to t. Well, you get a over b squared. Anyway, we can evaluate that. Here's the expected payout or the mean payout. Almost $87,000. We're going to have to charge pretty much for these insurance accounts. Let's modify it just a little bit and say we'll put a cap on it. Like, even if the damages are over 1 million, we're only going to pay out 1 million. So we have another, we can accommodate that with another little Dirac Delta function on it. This probability at 0 of a 0 payout was 0.8. This probability of $1 million payout is that 2%. So now we've got this PDF. I could write it this way, breaking it up, that like this for your argument between 0 and 1 million. And it's 0 if it's less than 0 or more than 1 million. And we now know our A and B. So how do we evaluate this expected? Well, remember we multiply the PDF by X. This is a sum, so we get 0.8 X, the Dirac Delta function. Had to do these out of order. The 0.2 times X, that Dirac Delta function. This one now has the A. It's not centered at 0. It's centered at 1 million. And then this guy for X between 0 and 1 million. So, okay, what's this evaluate to? Well, the A here is like this. But it's centered at 0. So plug in 0 for X, you get 0. This guy evaluates to 0. This guy will evaluate to 10 to the 6th. I got the 0.02 in front. So that's what that guy is. And for this mess, I had to use a table. We could evaluate it. Putting that cap took us down to 78,000. What was it before? 87. We went from 87 down to 78. Still a pretty payout. But anyway, that's mixed distributions. It's that